Chapter 2, Section 4, Digging Deeper, Metamorphic Rocks, Formation of Metamorphic Rocks. In the Investigate, you looked at what properties geologists use to classify metamorphic rocks. You then classified several samples. You also used a model that showed how rocks change their shape or deform during metamorphosis. Finally, you analyzed data on a geologic map to locate metamorphic rocks in your local area and region. Sedimentary and igneous rocks can be turned into metamorphic rocks. To do so, they need to be subjected to high temperatures and/or pressures. The process is called metamorphism. Metamorphism. The changes occur while the rock is still solid. The temperature of the rock is not so high that part of the rock melts. If the temperature becomes too high, part of the rock melts to form magma. The magma later cools to form an igneous rock. Crystals of a mineral can grow only in a certain range of temperature and pressure. Suppose a mineral crystal in a rock is subjected to the high temperatures and pressures outside of this range. When this happens, metamorphosis occurs. The mineral crystal is changed into crystals of one or more different minerals. This is why the minerals in a metamorphic rock are usually very different from the minerals in the original rock. However, a few common minerals, such as quartz and calcite, do not change form. When a limestone is metamorphosed, the calcite continues to exist. However, the crystals grow to be much larger. All evidence of the original features of the limestone is destroyed. For example, there is no more evidence of fossils. Geologists have learned a lot about metamorphic rocks in labs. They use special furnaces. These furnaces can be heated to extremely high temperatures. They are also under tremendous pressure. These are the temperatures and pressures under which metamorphic rocks can form. Using these studies, the geologist can infer the temperatures and pressures in Earth when the rocks were formed. Recall that every rock tells a story. Metamorphic rocks have their own story to tell. The temperature of a rock can be increased in two ways. Rocks can be buried deeper and deeper in Earth. This can happen by deposition of a very thick layer of sediment on top of the rock. This can happen by deposition of a very thick layer of sediment on top of the rock. It can also happen by movement along faults. Very thick masses of rock are shoved on top of the rock. As the rock is buried, its temperature gradually increases. This is because the temperature in Earth increases with depth. Enormous volumes of rock can be metamorphosed in this way by deep burial. This is the most important kind of metamorphism. It is called regional metamorphism because large regions of Earth's crust can be affected in this way. Figure 1 is a diagram explaining regional metamorphism. So here's the surface of the Earth up here, and then as you increase in depth, you also increase in pressure. So it's showing that the pressure goes up as the depth increases, and then as your temperature increases, so there's really three variables here. You have your temperature, depth, and pressure, and then depending on where the ranges of those are, you have the different types of metamorphic rocks. And then you reach a temperature where they just melt. So you have regional metamorphism here, and then thermal metamorphism here. All right. The temperature of a rock can also be increased if a body of magma passes near the rock. As the magma cools, the surrounding rock is heated. This can metamorphose the rock. As before, the minerals recrystallize but do not melt. Okay, so they want us to look at figure 2 for that. Figure 2, right here. Okay. As before, the minerals recrystallize but do not melt, as shown in figure 2, which shows that when an igneous rock intrudes another rock, the intense heat of the intrusion can result in the metamorphism of the surrounding rock. This is known as contact metamorphism. So here's an example of contact metamorphism. All right. If the intrusion is small, only a thin layer of the surrounding rock is metamorphosed. However, very large intrusions, such as the emplacement of a batholith, can metamorphose a large amount of rock. Surrounding rock for thousands of meters away from the intrusion can be changed. The further away from the intrusion, the less the degree of metamorphism. This type of metamorphism is more localized and is known as contact metamorphism. So here's the contact metamorphism right here. And then they said that as you get further and further away, it just becomes a separate type of rock. But the area of the rock around here is known as contact metamorphism. All right. Deformation and metamorphism. Rocks become highly deformed during regional metamorphism. Deformation is caused by stress. It can cause minerals to move around and become concentrated in layers. In Part B of the Investigate, you used a model that illustrated the deformation of a rock by shearing. The same thing happens, usually even more so, when rock is sheared by forces within Earth. This is especially common in subduction zones where one lithospheric plate slides down beneath another. You saw in the Investigate that when a material is sheared, lines or planes within it become more parallel. This is called transposition. In many metamorphic rocks, all kinds of features and structures are smeared out by transposition to become nearly parallel planes. The layering you see in a metamorphic rock may not have anything to do with the layering in the original rock. Forces within Earth can also stretch or compress the rock. In some metamorphosed conglomerates, the pebbles are stretched into a shape similar to a test tube. Foliation in metamorphic rocks. Some sedimentary rocks contain a high percentage of very fine flakes of mica minerals. These include claystone, mudstone, and shale. These rocks become metamorphosed first to slate. Then they become phyllite, and then schist. It depends on the intensity of metamorphism. You looked at the classification table in the Investigate. You notice that all of these rocks tend to split easily along parallel planes. This is because the mica minerals in the rock have grown to be parallel to one another. This causes weakness in the direction parallel to the planes of the mineral grains. The parallel growth develops for two reasons. First, the mica minerals grow with their planes perpendicular to the direction of greatest force on the rock. Second, when the rock is sheared, the mica grains tend to become parallel, as you read earlier. The tendency for a metamorphic rock to split along parallel planes is called foliation. Foliation, as shown in the photograph in Figure 3, is a major feature of many metamorphic rocks. Figure 3. This gneiss is an example of a strongly foliated metamorphic rock. Okay. And you can see it. I mean, you can see the parallels. You can see those parallel lines so that when it breaks, it also breaks off in that pattern. Okay. The protoliths of metamorphic rocks. The rock from which a metamorphic rock is formed is called the protolith. Both sedimentary and igneous rocks are protoliths of metamorphic rocks. The protolith can also be older metamorphic rock. Geologists are always interested in trying to figure out what the protolith of a rock was. Sometimes this is easy. For example, a quartzite probably started out as quartz sandstone. Marble probably started out as limestone. However, it is sometimes very difficult to guess the protolith of a metamorphic rock. Here's quartz sandstone, and here's quartzite. Quartz sandstone has kind of a rough texture. Quartzite has a sugary texture. Metamorphic rock units. Metamorphic rock units vary greatly in their makeup. Their shapes are more complex than those of sedimentary and igneous rock units. The reason is that metamorphism is usually accompanied by large-scale changes in the shape of the rock units. This happens in places like the roots of mountain ranges as they get pushed upwards. These changes take place by processes like folding and faulting. You will learn about folding and faulting in the next section. In some areas, sedimentary or igneous rock units change slowly into metamorphic rock units. This is because the intensity of metamorphism usually changes gradually from place to place. You should not be surprised if you see these slow changes on a geologic map. In one place on the map, you might see a rock unit called Smithtown limestone. Then it changes gradually to Smithtown marble in another area of the map. Igneous rocks. Crustal composition by volume. Igneous rocks take up 65% of the volume. Sedimentary rocks take up 11%, and metamorphic rocks take up 24% of the crust volume.